Good morning, and welcome to MAE 106. This is Discrete Mathematics with Probability. My name is Richard Kowar, and good morning to everyone in the chat. It's good to see everyone attending. Exactly. And today's lecture is lecture 24. We're almost, we've passed the midpoint now. We're almost finished. But this is lecture 24, and this is using counting techniques to calculate probability. So in this, we're going to use results that we learned from combinatorial analysis so that we don't need to actually write out or enumerate all those possibilities when we're calculating probabilities. So while we had problems in the previous section, like with sets, and we were dealing with permutations and combinations, and it kind of looked silly when we were looking at the number of ways letters of a city like Kingston could be rearranged. But those theorems and those results that we had looked at are important when we're calculating probability. We need to know things, or the total number of ways an event can happen, before we can even think of trying to predict the likelihood of something happening. So let's use an example. So this whole section is going to be about examples. And so our counting techniques, just as a refresher, we had permutations. And so those are arrangements where the order matters. So we would have like n permute r. So you can write that as n factorial over n minus r factorial. The other one that we have is combinations. And that's where order does not matter. And so there's our n choose r. There we go. So those are kind of the two main formulas that we have to kind of keep in mind. So let's start off with permutations. So I think the example that I use in the textbook is about a monkey sitting at a typewriter, and the monkey is going to start to hit random keys. And okay, so let's say here's the monkey at a typewriter. And the animal will hit keys at random. Let's assume that they're all uppercase letters. And let's say that you also can hit the space bar. So then the question can be, was the probability that the monkey types to be, I guess the first two words of that famous soliloquy, in the first 5 characters. So we'll let E be the event. That he types to be. So there's only one way to do that. And so the number of outcomes in that is 1. Okay. S is all the possible ways to type five characters. So again, we'll assume a uniform sample space meaning that each outcome is equally likely. Okay. So the number in the sample space, how many choices do we have for the first character? Just in the chat, how many choices do we have for the first character? Okay, so I have one person saying 26 and the other saying 27. Why 27? Okay, 28. Okay, why 28 then? Yes, plus the spacebar, exactly. Yeah, because there's the upper keys. So we're going to say uppercase, that's 26 plus 1. And we consider a space to be a character. So again, then there's 27 choices. So then we have 27 for the first character. There's 26 letters in the ABC. Yes, there's 26 letters. Last time I checked. Okay. And then you would have 27 again for the second. And you would have 22nd for the third, 27 for the fourth one, here's 27 for the So 1, 2, 3, 4, 5. So that's 27 to the 5th. Okay. So then the probability is that the monkey types to be in the first 5 characters is, so it's the probability of E. So you can write that as, so we have, there's one outcome that we want out of 27 to the 5th. So that's good enough? Yes, exactly. 27 to the 5th. Okay. And if you want to know what that is, like numerically, let's pull out a calculator. 27 to the 5th. $14,348,907. So again, I have a calculator. I don't expect you to use the calculator on that. If we're on a test, I would be expecting something like that. I would be 1 over 27 to the 5th. Okay, and if I, which is a very, very small number, it's approximately 1, 2, 3, 4, 5, 6, 7, 8. So a very, very slim chance. Okay, let's do number 2. So we had done permutations. Let's move on to combinations. Okay, so here in Ontario, we have the Lotto 649, which is pick 6 numbers from the set 1, 2, 3 all the way to 49. So again, I can let E be the event that you have the winning ticket. And how many ways is there to have a winning ticket? Well, you need to make sure that the first number was picked right. You need to make sure that the second number was picked right, the third, the fourth, the fifth, and the 6. So again, there's just one way. So again, assuming a uniform sample space, how many total possible, or how many possible tickets are there then? Okay, so there's 49. Okay, so we have a couple of them. So here are the answers. I got a couple. So I had the numbers. Oh, and so yes, with a lottery ticket, that's a good question. The numbers don't repeat. So yes, so you pick the 6 numbers from 1, 2, 3, 4, 5, 6, 7, and without repetition. Okay, so we said that it's without repetition. Okay, so we got a couple. I'll write down. So we have 49 to the 6th. We had 49 times 48 times ... We had 49 choose 6. Okay, so this one would be that over here, that would be assuming that I had 49 choices for the first one. I would have 49 for the second, ... all the way up to the 9th one. So there's the second number all the way up to 6. But this one says without repetition. So you can't really have that because you would have one less each time you're doing your choice. Okay, so that one we can exclude. So, oops, moving down to this one. This one would be without repetition. To the 6. 47, 46, 45, 44. Oops. That's the cap. Okay. But now, this is a permutation. And in this case, this is where the order matters. Now, when we do a lottery ticket, we usually do write it in ascending order. So like if I pick some numbers, I have 9 and I pick 18, 21, 33, 24, 3, 4, 5, one more, let's say 2. If you said that the order matters, if I change the order of this, this would be considered a completely another ticket. But that's not the case. When we talk about the lottery, we usually just think of it in, we just pick those numbers, and by convention, we write them in ascending order. So we would write that as 2, 9, 18, 21, 24, 33. Because we just picked them, basically they're balls, and they just come out. So you could do a draw. You would get the 9, the 18, the 21, the 33, the 24, and then the 2. And then what they would do is they would rearrange it so that you would write it in ascending order. So we don't really care in which order that they came in. We just care about what the actual numbers are. So you can say this without repetition. And the order does not matter. Yes, it does not matter for the, I've never, yep. So here we have the combinations. So there would have been a hint that we were going to be using combinations. So it's not the second one, because that would be if the order mattered. And the last one that we have is 49, choose 6. And this is the one where the order doesn't matter. There we go. $49, choose 6. So we have 49, and then we have 6. 49 minus 6. And this is already going to be a large number, so. But no, this is good that people ask, because these are common answers that, well, common incorrect answers, and we don't want to have those on the test. So it's good that we get all the different ones and why this one is the correct one. Wow. It's going to be a big number. Okay, so I'm not even going to do that by hand. That's quite a big number. I already know how big it is roughly. It should be about 13.9 million, but so you can pull out a calculator and you type it out: 49, 48, 47, 46, 45, 44. So in the top, we would have 10 million. 68,000. Oh no, it's even bigger than, I guess that's 10 billion. 68 million. 347,520. We know what 6 factorial is. That's 720. Divide it. And so we get 13,983,816, which is a large number. Just to give you an idea, if you did have with repetition, that's 49 to the 6, 49 to the 6. So that's approximately 13,841,287. 201, and that one would be 49 permute 6. Okay, so here I only have 13 million. Over here I have, that's thousands, millions, billions. Thousands, millions, billions. So I'm in the realm of millions, and over here, if you start to allow repetition, or where the order does matter, then we're getting into the order of billions of arrangements or possible tickets. So the fact that we pick without repetition and the order doesn't matter, we get a smaller number of 13.9 million. So the probability of winning the Lotto 649 here in Ontario is 1 over 983,816. And that's a very, very small probability. Again, it's 0.000. So 1, 2, 3, 4, 5, 6, 7, and okay, very, very small chance. Coincidentally, you would have a better chance of getting struck by lightning than winning the Lotto 649. How would we want that to look on the test? So on a test, you would just write it. (49)6 over 1. Or, like you saw right here, this is a great multiple choice question. You could have multiple choices for that. So you could have 49 choose to the 6, 49 times 48, or 49 choose 6. Exactly. Again, because 49 choose 6 is a big number. Okay. Okay, so let's say that you don't have a monkey that sits at your typewriter to type out an assignment, so you're going, this is not very applicable to me. Another person says, I don't play the lottery, so again, this isn't applicable to me. But how about this one? Maybe you might come across some usefulness for this. I call this the lazy professor problem. So let's say that there's an assignment and it has, let's say, 10 questions. And so in order to save time, what the professor, or let's say me, I'm going to only correct 3 of them. So you mark 3 questions. And let's say that these are selected at random. Okay. So I'm going to mark only 3 of those questions. I'm going to select them at random. So let's say your assignment has only let's say 2 wrong, or let's say incomplete. Ran out of time, didn't have just ran out of time, just submitted it. What is the probability that at least one wrong or incomplete question is selected? Okay. So again, we're going to assume, because it's selected at random, we're going to say all equally likely to be selected. So then the sample space, let's start off with that one. How many possible ways can I pick 10 questions? Pick 3 questions from 10. So it would be 10, choose 3. So picking, oops, not 10, picking, yes, 3 questions from 10. And the order doesn't matter. candidates without repetition. Can you say without replacement, like picking it and then putting it back, or repetition? So 10 minus 3 should give you 7 factorial. 10 times 9 times 8 times 7. So that should give you 120. Okay, so there's 120 possible ways. We're going to assume that they're all equally likely to occur. Okay, so now we need to calculate the cases that we want. So again, we'll let E be the event. That at least one wrong, incomplete question is selected. So this could be, we could do this in using direct reasoning. And that's where you would take cases. And that's where you would look at one wrong question, or you could do two wrong. So there's two cases. Or the other way we could do it is indirect. That's where we'll take all the possible ways and remove what we don't want. Okay, and that's what we're going to do. We're going to do indirect reasoning. So what we're going to do is we're going to look at all the possible, which is the probability is 1 minus the probability of E. And that would be the complement. So this is not what we want. What we actually want is the probability that this. So what we can do is instead we can calculate the complement. So 1 minus the probability of E complement. And what E complement means is that it's the event that no incomplete questions are selected. Okay? So we can actually calculate what the number of cases for E complement. How many ways can I select questions where there's no incomplete or wrong questions. I believe it's the first one. It will be, you're right. So there was 10 original choices, right? But we don't want to include the 2 incomplete or incorrect questions, but we're still going to pick 3, right? So that will leave us with 8, choose 3. I don't think it's 10, choose 8. Because if you had 10, those are 10 questions, and then you'd be picking 8 of them. So no, in this case, what we want is there'll be 8. Those 8 are all correct. And from those 8, we're going to pick 3. Give me a second. 3 goes into 6 twice. The 2's cancel, so I'm just left with 8 times 7, which is 56. Good. So then the probability of E 1 minus, and so the probability of E complement would be 56 over the total number of cases, which is 120. And so 120 minus the 56. Okay, so you can think of this as 20 over 120. 64 over 120. And so that's approximately 53.3%. %. Okay, so that was doing it using indirect reasoning. So some people might not have done it that way, using indirect reasoning. So let's use direct reasoning. So let's do it with those cases. Let's hope that I get the same answers that we got in the indirect. So we know we're going to still carry over our calculation from the sample space. So we knew that the sample space was, we had 10 questions, we're choosing 3, and that worked out to 120. It's a lot lower than I guessed it would have been. Well, yeah, I'm interested to find out. Let's try. Basically, what we're going to do is check our answer, because maybe we did something incorrect. So let's try doing it with direct reasoning. We'll take cases. So we'll have case 1 where there's 1 incorrect. So if there's 1 incorrect, that would mean that you would have 9 questions and you're going to choose 2 of them, multiplied by, you have the 2 incorrect and you're going to pick 1. Oh, no, I made a mistake. Should be 8. So over here you can see that this should be 10. 8 plus 2 gives me 10 questions. And 2 plus 1, that's the 3 selected. So over here, that's where we do we're going to make our correct choice. Sorry, our correct question selection, and this one would be the incorrect. So 8 choose 2 is 28. 2 choose 1 is 2. And then that gives you the 56. Case 2, there would be 2 incorrect. So again, I have 8 correct questions. I want to pick 1 of those. I would have 2 incorrect questions. I'm going to pick all of them. This makes it a little bit easier. So I have 8 choose 1 is, so there's 8 questions. There's 1 I'm going to pick, so there's 8 ways to do that. I have 2 questions. I'm going to pick all 2 of them. There's only 1 way to do that, so that's 8. So adding up those 2 cases, I get 56 plus 8, which is 64. Okay. So, therefore, the probability of event E is the number in E over the number of the sample points. So I get 64 over 120. Okay, and again, that is still approximately 53.3%. Okay, so what we do then is we look what we did in the indirect. So you can think of it over here. Here's my Venn diagram. Here's E, and here's E complement. So over here, E, at least 1 wrong. And the complement is none. Wrong. Okay, so again, looking here, the probability that I calculated using the indirect reasoning is the same as what we got with the direct reasoning. So just as a little remark, two methods yield the same answer. So that's good. So we're confident. Perfect. Okay, again, if you have any questions about the material that we've covered, feel free to send me an email at my RMC account. You could say all three questions are correct, but isn't it at least one is incorrect? Yes, because that was what the original question was asking. What is the probability that at least one wrong or incomplete question is selected? Yep. Perfect. And that's page 4. And this will be posted to our Moodle page. Thank you everyone for tuning in, and have a great afternoon.